All the circuits we've studied so far in this model are simple circuits, series or parallel, where in series circuits, a current or a single electron would travel through every single resistor, or in parallel, a single electron would travel through only one resistor. As you see on our screen here, this is not a simple circuit, so it's a complex circuit. It's basically a combination of series and parallel connections to make up a circuit. The purpose of this video is to introduce you to how to analyze these complex circuits. By the end of this video, you should be able to find the equivalent resistance of this entire circuit, and then there will be a second video showing you how to find the voltage and the current in each resistor, as well as through the battery of your circuit. So let's start out by analyzing what connections we have. Thinking about these 5 resistors we see in the circuit, 2 resistors are in series if the current is forced to travel through both of them. In other words, if the current travels through one, it must travel through the other, no matter which order we go in. For example, resistors B and C here are in series with each other, because if the current travels through B, then it has to travel through C. Likewise, if the current travels through C, then it's forced to travel through B. Resistors A and E are also in series with each other, because if current travels through A, it must travel through E, and if current travels through E, it must travel through A. There is no combination in the circuit we see here that is a parallel combination. The reason for that is if we're looking at our combination kind of like right here, some may say that B and D are parallel to each other. The reason that's not the case is if we look at the current that goes through B, it also has to go through C before recombining with the current that goes through D. When we have a parallel connection, that current will only go through a single resistor before combining with the other current it split from. So keeping in mind that B and C are in series with each other, we're going to go through the steps that it takes to find the equivalent resistance of our circuit. I'm going to go back and label these resistors as I had them labeled on the previous slide. A, B, C, this was D here, and this was E. The first thing I'm going to do is recognize that B and C are in series with each other, as previously mentioned. And so I'm going to combine these 2 resistors to form a single resistor with the same resistance as those 2. Since they're in series with each other, I know that my equivalent resistance can be found by adding them. So I'm going to add the resistance of B plus the resistance of C. So I have 1.5 kiloohms plus 1.5 kiloohms, which I know gives me 3 kiloohms. The next thing you must do is to draw a new circuit diagram once you've combined resistors. This may seem like an unnecessary step until you get to the next video where we're looking at some VIR charts, and then it'll be really important and you'll understand why we do this. So notice that I've just drawn one resistor up here. I'm going to call this resistor BC since I combined B and C to get that resistor. And it has an equivalent resistance of 3 kiloohms. I'm going to repeat this process again, combining 2 resistors that are either in series or in parallel with each other, but paying attention to my new circuit diagram rather than my original one. If I look at this new circuit diagram, I notice that I actually have 2 resistors that are in parallel with each other. That's my new resistor BC, as well as my resistor D. The reason these are in parallel is as the current enters this junction right here, some of it travels up and goes through BC, some of it travels downward and goes through D. It recombines at this junction right here, And between those two circled junctions, my current has only traveled through one resistor. Since that's the case, I can combine those in parallel with each other. We know the equation for a parallel circuit is 1 over the equivalent resistance is 1 over, we often said R1, but I'm going to put RBC here, plus 1 over the resistance of D. So basically we're adding 1/3 plus 1/6 and then taking the inverse of those. And when I do that, I end up with a resistance of 2 kiloohms. Now I'm going to draw a new circuit diagram with a new resistor in that location. So this is still resistor E over here, a 3 kiloohm resistor. This is resistor A, a 1 kiloohm resistor. And this is now resistor BCD, since I combined all three of those. And it is a 2 kiloohm resistor. I've now gotten to the point where I have a simple circuit, because this is now a series circuit. So my equivalent resistance can be found simply by adding these three resistances. 1 plus 2 plus 3 kiloohms gives me a total equivalent resistance for my circuit of 6 kiloohms. Again, that process that we just went through to find that equivalent resistance required us to combine two resistors at a time, and every time we combined those two resistors, we drew a new diagram. Now, on my previous slide, I had mentioned that resistor A and E were also in series with each other. So I could have started by doing that, and that there would have been nothing wrong with doing that. I still should have ended up with the exact same answer as I did here. We'll be doing lots of practice with this, and probably the most challenging thing with finding the equivalent resistance is making sure that you choose the correct resistors to combine. So we'll make sure we practice that a bunch in class.